Hi everyone, I'm Period-Lap-Loi Chung from the National Center for Research on Earthquake Engineering and Departments of Civil Engineering, National Taiwan University and National Cheng Kung University. This is my name in Chinese, Zhong Li Lai. Welcome to the course Introduction to Seismic Design of Structures. This unit is about fundamental vibration period of structures. And let us learn some terminology first. Fundamental vibration period, in Chinese, 基本振动周期 portal frame, 门型构架 seismic force, 地震力 approximate fundamental period given by seismic design codes, 近似之基本振动周期是从耐震设计规范提供的。Fundamental vibration frequency, 基本振动频率 Free body diagram, 自由体图 Mass, 质量 Stiffness, 硬度 Inertial force, 惯性力 Restoring force, 回复力 External force, 外力 Free vibration, 自由振动 Initial displacement, 初始位移Initial velocity, 初始速度 Laplace transform, 拉式变换 Inverse Laplace transform, 拉式力转换 Derivative, 导数 And here is a portal frame. EC is the elastic modulus of the column. IC is the moment inertia of the column. HC is the height of the column. EB here is the elastic modulus of the beam. IB is the moment inertia of the beam. LB is the span of the beam. My question is that, what's the stiffness of this portal frame? And what's the fundamental frequency, fundamental vibration period of this portal frame? And we have some assumptions. We assume that all the mass lump to the beam. That means that the weight of the beam and the slab is assigned to be M, and the weight of the column is neglected. And my question is that, what's the stiffness of the portal frame, and what's the fundamental vibration period of the portal frame? Another question is that, Taipei 101 is the tallest building in Taipei. What is its fundamental vibration period, T? Fundamental vibration period of a structure is defined as the time taken for one complete cycle of vibration, and the unit of period usually used as here means second. If the structure with higher stiffness, then the vibration period may be shorter. Why is it so important to study the fundamental vibration period of a structure? There are two reasons. Structural responses, including displacement, velocity, and acceleration, depends on vibration period. The longer the period in general, the larger the displacement, and the smaller the acceleration. And seismic forces depends on structural responses. In general, the higher the acceleration, the higher the seismic force. The second reason is that the development of deformation capacity depends on vibration period. In general, the longer the period, the better the development. And seismic force depends on the development of deformation capacity. Usually, the better the development of the deformation capacity, the lower the seismic force. Therefore, we have two reasons to learn about fundamental vibration period of structure. And from seismic design codes, approximate fundamental period are given. If the structure is a steel structure with moment-resisting frame, or we have rigid joint, and no non-structural rigid wall, no shear wall, and no other lateral force resisting members, then its approximate fundamental period given by seismic design code T equal to 0.085 Hn to the power 3/4. Hn is defined as the building height, which is the roof elevation from the base. And from this equation, we have the higher the building height, Hn, the longer the fundamental period. That means that when the structure becomes higher, it becomes softer, so that the vibration period becomes longer. And if the structure is reinforced concrete structure or steel reinforced concrete structure with moment resisting frame and no non-structural rigid wall, no shear wall, no other lateral force resisting members, then its approximate fundamental period given by the seismic design code T equal to 0.07 Hn to the power 3/4. If we go to the previous slide, the coefficient here is 0.085 and the coefficient here is 0.07. That means that for structure with the same building height Hn, steel structure has a longer fundamental period than reinforced concrete structure, because for steel structure the coefficient is 0.085. For reinforced concrete structure, the coefficient is 0.07. Therefore, steel structure has longer fundamental period than reinforced concrete structure. And for other structures, that means that the structure has non-structural rigid wall, has shear wall, or other lateral force resisting members, then its approximate fundamental period given by seismic design code T equal to 0.05 Hn to the power 3/4. For structure with the same building height, structure with walls has shorter fundamental period than that without. And here, the coefficient here is 0.05. That's the structure with walls. And if we go back to the previous slide, it's 0.07 for reinforced concrete structure with moment resisting frame. If we go back to the previous one, it's 0.085 for steel structure with moment resisting frame. Therefore, for structure with walls, the fundamental period is shorter. And from fundamental period, we can derive fundamental vibration frequency. That is F equal to 1 divided by T. Therefore, frequency is the reciprocal of the period. The longer the fundamental period, the smaller the seismic force. Because when the fundamental period is longer, the structure becomes softer. Therefore, the seismic force becomes smaller. On the other hand, the shorter the fundamental period, the larger the seismic force. Because when the fundamental period becomes shorter, the structure becomes stiffer. Therefore, the seismic force becomes larger. And here, if we let the structural displacement xt equal to d sine omega t, and omega is the angular frequency, its unit is radian per second, and omega equal to 2 pi f, and f here, the unit is hertz or cycles per second. And d here is the amplitude of the displacement. Omega here is the frequency of the displacement. And if we take the first derivative, then we can have velocity, structural velocity, equal to d omega cosine omega t. And omega is also the frequency of the structural velocity, but the amplitude becomes d times omega. And if we take the second derivative of this displacement, then we can get the acceleration, structural acceleration, at. At equal to d times omega squared sine omega t. Omega is also the frequency of the structural acceleration, and the amplitude of acceleration becomes d times omega squared. For structure with the same displacement amplitude d, the higher the frequency omega, the larger the acceleration a, and the larger the seismic force. because here you can observe from here that the amplitude of acceleration equal to d times omega squared. That means that if we have higher frequency, then the amplitude of structural acceleration becomes higher, and the seismic force also becomes higher. And if we let structural acceleration at equal to a sine omega t, and omega is the vibration frequency, and a is the amplitude of the structural acceleration. And if we integrate the acceleration, we can have the structural velocity, Vt. Vt equal to minus a divided by omega, cosine omega t. Then a divided by omega becomes the amplitude of the structural velocity. And if we integrate again, we can have the structural displacement equal to xt equal to minus a divided by omega squared, sine omega t. Omega is also the frequency of the structural displacement, but the amplitude of the structural displacement becomes a divided by omega squared. And you can observe from this coefficient here, the amplitude here, if the frequency becomes higher, the amplitude of the displacement becomes lower. Therefore, for structures with same acceleration amplitude A, the higher the frequency, the smaller the displacement amplitude x. Well, now if we consider a structure, a single degree of freedom structure, that can be modified by a system with mass and spring. And m is the mass of the structure, and k is the stiffness of the structure. And it is a single degree of freedom structure because the displacement of the structure can be described by only just one variable, xt here. And ft here is the external force for this single degree of freedom structure. If there's a displacement to the right, xt, and we can have the free body diagram here. And because the structure moved to the right with the displacement xt, therefore the restoring force equal to k times xt, and ft is the external force. And from the Newton's second law, F equal to ma. F here means the resultant of all the forces. Therefore, the resultant force equal to Ft minus kxt. Ft here is positive because the direction of the force is to the right. And kxt is negative because the force points toward to the left. Therefore, the resultant force equal to Ft minus kxt equal to ma. A is the acceleration of the mass. And A is also the second derivative of displacement. Therefore, ma equal to mx double dot equal to F minus kxt. If we move minus kxt from the right-hand side of the equation to the left-hand side of the equation, then we can have mx double dot plus kx equal to ft. And this equation is called the equation of motion of the structure. And we can observe from here that the equation is a second-order differential equation. Mx double dot plus kxt equal to ft. And it's an equation of motion of undamped because there are no damping in the structure. And it's a single degree of freedom because the displacement of the structure can be described by only just one variable. And from engineering mathematics, is an ordinary differential equation. M here is the mass of the structure, K is the stiffness of the structure, M times x double dot is the inertial force, and kxt is the restoring force, and ft is the external force. And therefore, the motion equation can be considered as equilibrium equation of the structure. And this equation is second order. Because of the second derivative, it's non-homogeneous because there's a forcing function ft here. That means that in addition to x and its derivatives, there's also a function, there's a function of t. Therefore, it's non-homogeneous. And this is ordinary differential equation with constant coefficient, because the coefficient here, m, the mass, is constant. It does not vary with time. And k, the stiffness of the structure, is also constant. It does not vary with time. Okay, we consider free vibration first. Free vibration means that there's no external force. Ft equal to 0. Therefore, here, no external force is applied to the structure. Okay, let's consider the free vibration. Therefore, the motion equation becomes mx double dot plus kxt equal to 0. And this second order, because of the second derivative, is homogeneous because there's no forcing function here. And this ordinary differential equation with constant coefficient, because m and k are constant. They do not vary with time. And if we divide the whole equation by m, then we can have x double dot plus k divided by m times x equal to 0. And k divided by m can be considered as vibration frequency. Omega 0 equal to square root of k divided by m. Therefore, finally, we can have the equation as x double dot plus omega 0 square x equal to 0. And if we consider the vibration frequency for structure with the same mass m, the larger the stiffness k, the higher the frequency k, the higher the frequency f, and the shorter the period t, because vibration period is the reciprocal of the frequency. For structure with same stiffness k, the larger the mass m, the lower the frequency, because the denominator is larger, then the frequency becomes lower. The frequency lower, therefore the period becomes longer. Okay, we are going to solve the motion equation of a structure under free vibration. X double dot plus omega 0 square xt. And from ordinary differential equation in the textbook of engineering mathematics, we can let xt equal to exponential lambda t. And then we take the first derivative, then we can have the velocity equal to lambda exponential lambda t. And then take the second derivative, we can have x double dot equal to lambda square exponential lambda t. Then we substitute xt into the motion equation. X double dot t into the motion equation. Then we have lambda square x double dot equal to lambda square exponential lambda t plus omega 0 square xt equal to exponential lambda t. And after observing this equation, we find that exponential lambda t is the common factor. Therefore, we take this common factor out, and then we can factorize the left-hand side of the equation. Because exponential lambda t will not be equal to 0. Therefore, lambda square plus omega 0 square must be equal to 0. And there are two roots for this equation. The full first root, lambda 1, equal to minus omega 0 I. And I here is an imaginary unit equal to square root of minus 1. And the second root equal to omega 0 I. Therefore, we have two roots for this equation. If we substitute lambda 1 back to here, then this is the first solution of this motion equation. And if we substitute back lambda 2 back to this equation, then we have the second solution for the free vibration. From the first solution and the second solution, we combine all of them. Then we can have the general solution for the displacement. Xt equal to C1 exponential lambda t plus C2 exponential lambda 2t. And C1, C2 are two coefficients. Lambda 1 equal to minus I omega 0. Lambda 2 equal to I omega 0. And from Euler's equation, we can have exponential I theta equal to cosine theta plus I cosine theta. Therefore, exponential minus I omega 0t equal to cosine omega 0t minus I sine omega 0t. And exponential I omega t equal to cosine omega 0t plus I sine omega 0t. And from this term, we can have the common factor, cosine omega 0t. Then therefore we take the cosine omega 0t out of the equation. Then we have the coefficient C1 plus C2. Another common factor is sine omega 0t. And the corresponding coefficient R, and the corresponding coefficient is I times minus C1 plus C2. If we rename C1 plus C2 equal to small c1, I minus c1, I times minus c1 plus c2 equal to small c2, then we can rewrite the solution xt equal to c1 cosine omega 0t plus c2 sine omega 0t. And we know that the displacement should be a real function, and cosine omega 0t is a real function. Sine omega 0t is also a real function. Therefore, the coefficients C1 and C2 are real number. Therefore, the solution here, everything is real. Real function, real number. Once we have the solution for the displacement, xt equal to C1 cosine omega 0t plus C2 sine omega 0t. Then we take the first derivative. Then we can have the structural velocity x dot equal to minus C1 omega 0 sine omega 0t plus C2 omega 0 cosine omega 0t. And take the second derivative. Then we can have the structural acceleration x double dot equal to minus C1 omega 0 square cosine omega 0t minus C2 omega 0 square sine omega 0t. Then we have two unknown coefficients, C1 and C2. Therefore, we need two conditions to solve for C1 and C2. And these two conditions are called initial conditions. If we have the initial displacement, x of 0 equal to x0, and also we have the initial velocity, x dot of 0 equal to 0, then we can have two initial conditions. One is initial displacement, another is initial velocity. From the initial displacement, x of 0 equal to x0, then we can substitute t here with 0. Substitute t here with 0. And cosine 0 equal to 1. Therefore, C1 times 1. Sine 0 equal to 0. C2 times 0 equal to x0. Then we can solve for C1. And C1 equal to x0. And then from the initial velocity, x dot of 0 equal to 0. Then we substitute t here by 0. Sine 0 equal to 0. Cosine 0 equal to 1. Then solve this equation. We can have C2 equal to 0. Once we have solved C1 and C2, and we substitute C1 and C2 back to the displacement, then we can have the structural displacement xt equal to x0 cosine omega 0t. Substitute C1 and C2 back to the velocity, then we can have the structural velocity x dot equal to minus x0 cosine omega 0 sine omega 0t. And if we substitute C1 and C2 back to the second derivative, then we can have the structural acceleration x double dot equal to minus x0 omega 0 square cosine omega 0t. Now we consider another case. Here, initial displacement 0 equal to 0, but initial velocity is non-zero. Therefore, x of 0 equal to 0, x dot of 0 equal to x0 dot. Then with the initial displacement, x0 equal to 0, then we have C1 times 1 plus C2 times 0 equal to 0. Then, therefore, we can solve for C1 equal to 0. And from the initial velocity, x dot of 0 equal to x0 dot. Therefore, we can have minus C1 omega 0 times 0 plus C2 omega 0 times 1. Then we can solve for C2 equal to x0 dot divided by omega 0. Once we have solved for C1 and C2, and we substitute the coefficients C1 and C2 back to here, here, and here, then we can have the structural displacement xt equal to x0 dot divided by omega 0 sine omega 0t. Then we can have the structural velocity x dot equal to x0 dot cosine omega 0t. And also, we can have the structural acceleration x double dot t equal to minus x0 dot omega 0 sine omega 0t. And we consider the third case. And here, initial displacement is non-zero, and the initial velocity is non-zero as well. Therefore, x of 0 equal to x0, x dot of 0 equal to x0 dot. And from initial displacement, x of 0 equal to x0. Then we can have C1 times 1 plus C2 times 0 equal to x0. Then we can solve for C1 equal to x0. And from the initial velocity, x dot of 0 equal to x0 dot, then we can have minus C1 omega 0 times 0 plus C2 omega 0 times 1 equal to x0 dot. Then we can solve for C2, and C2 equal to x0 dot divided by omega 0. Once we have solved for the coefficients C1 and C2, then we substitute to xt, and also to its first derivative, and also to the second derivative. Then we can have the structural displacement xt equal to x0 cosine omega 0t plus x0 dot divided by omega 0 times sine omega 0t. And the structural velocity x dot t equal to minus x0 omega 0 sine omega 0t plus x0 dot cosine omega 0t. And also we can have the structural acceleration x double dot t equal to minus x0 omega 0 square cosine omega 0t minus x dot x0 dot omega 0 sine omega 0t. For all the three cases, no matter the initial velocity is 0, or the initial displacement is 0, or both of them are non-zero, then we can solve the displacement, structural velocity, and the structural acceleration. In addition to ordinary differential equation, we can solve the equation by Laplace transform. And we would like to solve the same problem with two methods. If the solution are the same, that means that the methods are very reliable. XS, the capital XS, is a Laplace transform of small xt. And from the definition of Laplace transformation, we can have XS equal to the Laplace transform of xt. And from the definition is the integration from 0 to infinity, exponential minus st times xt dt. And this is the definition of Laplace transform. Okay, here's an example. If xt equal to exponential at, then we would like to find out the Laplace transform of this function. And from the definition of Laplace transform, xs equal to integrate from 0 to infinity, exponential at, exponential minus st dt. Then after integration equal to 1 minus 1 divided by s minus a, exponential minus s minus at. And the lower limit is 0, the upper limit is infinity. Let me consider the upper limit. When t tends to infinity, if s minus a is positive, then this term will vanish, will disappear. When t equal to 0 and this term equal to 1, therefore we have 1 divided by s minus a if s is larger than a. Therefore we have the Laplace transform of exponential at equal to 1 over s minus a under the condition that s is larger than a. And then here is another example. If xt equal to sine omega t, and then we would like to find out the Laplace transform of sine omega t. And from the definition, xs equal to integration from 0 to infinity sine omega t exponential minus st dt. And sine omega t can be expressed as exponential I omega t minus exponential minus I omega t, and then divided by 2i. From Euler's equation, exponential I omega t minus exponential minus I omega t equal to 2i sine omega t, and 2i is cancelled out. Therefore, this term equal to sine omega t. Then exponential minus st dt. And from the definition, from the result we derived before, the Laplace transform of exponential at equal to 1 divided by s minus a. And let us consider this term first. Now a becomes I omega. Therefore 1 divided by s minus a equal to 1 divided by s minus I omega. And then here a is minus I omega. Therefore 1 divided by s minus a equal to 1 divided by s plus I omega. If we sum up these two terms, we can have xs equal to omega divided by s squared plus omega squared. Therefore, we can have this result, the Laplace transform of sine omega t equal to omega divided by s squared plus omega squared. And here's the third example. When xt equal to cosine omega t, and t is larger than or equal to 0, and we would like to find out the Laplace transform of xt. And from definition, the Laplace transform is integration from 0 to infinity cosine omega t exponential minus st dt. And cosine omega t, from Euler's equation, we can have exponential I omega t plus exponential minus I omega t divided by 2, because exponential I omega t equal to cosine omega t plus I sine omega t, and exponential minus I omega t equal to cosine omega t minus sine omega t, and sine omega t cancel out. Then we have 2 cosine omega t divided by 2. Then we have cosine omega t. And also from the result of Laplace transform, we can have the Laplace transform of exponential at equal to 1 divided by s minus a. And here a equal to I omega. Therefore 1 divided by s minus I omega. And here a equal to minus I omega. Therefore we have the Laplace transform 1 divided by s plus I omega. Then we sum up these two terms. We can have s divided by s squared plus omega squared. Therefore we can conclude that the Laplace transform of cosine omega t equal to s divided by s squared plus omega squared. And also we would like to find out the Laplace transform of derivative, because for the motion equation of structure, we have the variable xt and also the second derivative, sometimes maybe the first derivative, so that we have the velocity and also the acceleration. And here x dot t is the first derivative of xt, that's the velocity. And its Laplace transform by definition is the integration from 0 to infinity x dot t exponential minus st dt. And here we consider exponential minus st as u, x dot dt as dv. And then from integration by part, here u is exponential minus st, and v is xt, and minus integration from 0 to infinity. And here v equal to xt, and du equal to minus s exponential minus st. And consider the first term first. And if t tends to infinity and s is positive, and this term disappears. And then we consider the lower limit. If t equal to 0, this term becomes 1, that's x0. There's minus x0 here. And here, because s is not a function of t, then it can be taken out from the integration. Therefore, we have s integration from 0 to infinity. Xt exponential minus st dt, and this one is the Laplace transform of xt. Therefore, equal to s Laplace transform of xt minus x0. Therefore, we can conclude that the Laplace transform of velocity equal to s times the Laplace transform of the displacement minus initial displacement. And we further consider the Laplace transform of second derivative. Second derivative is the first derivative of the first derivative. Therefore, from this property, the Laplace transform of x double dot equal to the s times the Laplace transform of x dot minus the initial velocity. And the Laplace transform of the first derivative equal to s times the Laplace transform of the variable xt minus the initial displacement. And after rearrangement, we can have the Laplace transform of x double dot equal to s squared Laplace transform of x minus s x0 minus x dot of 0. Therefore, we can conclude that Laplace transform of acceleration equal to s squared times the Laplace transform of displacement minus s times the initial displacement minus the initial velocity. And we are going to solve the motion equation under free vibration by Laplace transform with the initial condition x0, x of 0 equal to x0, x dot of 0 equal to x0 dot. And we take Laplace transformation to the motion equation. Therefore, xt, the Laplace transform of xt equal to xs. The Laplace transform of x double dot equal to s squared times x of s minus s times initial displacement minus initial velocity equal to 0. Therefore, after rearrangement, we can solve for x of s equal to s times x0 plus x0 dot divided by s squared plus omega 0 squared. And this is not the final solution. We would like to have the inverse transformation so that we can solve for xt instead of xs. Okay, by using partial fraction, x of s can be expressed in this way. x0 times s divided by s squared plus omega 0 squared plus x0 dot divided by omega 0 divided by s squared plus omega 0 squared. If we compare this term with the Laplace transform of cosine omega t equal to s divided by s squared plus omega 0 squared, and omega 0 here is substituted by omega 0. Therefore, the inverse transformation of this term is cosine omega 0 t instead of cosine omega t. And then we consider the second term here, omega 0 divided by s squared plus omega 0 squared. And if we observe the Laplace transform of sine omega t equal to omega divided by s squared plus omega squared, and compare these two terms, omega is substituted by omega 0, is replaced by omega 0. Therefore, the inverse transformation of this term is sine omega 0t. Then we can have xt, that's the displacement of the structure, equal to x0 cosine omega 0t plus x0 dot divided by omega 0 sine omega 0t. And you can compare the result obtained by ordinary differential equation in slide page 24. The results are the same. That means that no matter you solve it by ordinary differential equation or Laplace transform, you can have the same result. Therefore, using two methods with the same result, therefore we are very confident that this result is right. And here's an example. It's a single degree of freedom under free vibration. The mass of the structure M equal to 2,000 tons. The stiffness of the structure K equal to M times 2 pi square equal to 789.57 kilonewton per meter. Then we can have the natural frequency omega 0 is the square root of K divided by M equal to 2 pi or equal to 6.283 radian per second. And from omega 0 divided by 2 pi, we can have F0 equal to 1 Hertz. That's 1 cycle per second. And then we take the reciprocal of F0, we can have the natural period T0 equal to 1 second, because 1 divided by 1 equal to 1. Therefore, the natural period for this structure is 1 second. Given the initial displacement x of 0 equal to x0 equal to 0.1 meter, and the initial velocity x dot of 0 equal to x0 dot equal to 0. Therefore, the initial displacement is non-zero, but the initial velocity is 0. And then we solve the motion equation. We can have the displacement xt equal to x0 cosine omega 0t. And x0 here is 0.1, cosine omega 0 here is 2 pi. Therefore, the 0.1 cosine 2 pi t. The unit is meter. And structural velocity x dot t equal to minus x0 omega 0 sine omega 0t equal to minus 0.2 pi sine 2 pi t. The unit here is meter per second. And structural acceleration x double dot equal to minus x0 cos omega 0 square cosine omega 0t equal to minus 0.4 pi square cosine 2 pi t. And then we can plot the graphs for the displacement, velocity, and acceleration. And here's the graph. And we have to check whether the result is correct or not. First one, here is one cycle, and the one cycle here, for one complete cycle of vibration, it takes 1 second. Therefore, the period is 1 second, or the frequency is 1 Hertz, and it's the same as we expected here. The period is 1 second, the frequency is 1 Hertz. That means that to complete one cycle of vibration, it takes 1 second. Or we can say that it's a 1 cycle per second. Therefore, the frequency is 1 Hertz. Another way we have to check whether the plot is correct or not. And we can check the initial displacement, 0.1, as we expected. And also the amplitude of the displacement is 0.1 meter. That's what we expected. And then check the velocity. And here's 1 cycle. That means that to complete 1 cycle of velocity, it takes 1 second. Therefore, it's consistent with our natural period, 1 second, and it's consistent with our natural frequency, 1 Hertz. And check the initial velocity. Initial velocity equal to 0. And it's compatible what we expect. When we assign the initial velocity is 0. We assign 0 initial velocity. Then, therefore, the initial velocity is okay. And also check the amplitude of the velocity. Amplitude of the velocity v equal to 0.1 times 2 pi is about 0.6 something. And the unit is meter per second. And then we check the acceleration. The amplitude of the acceleration is 0.1 times 2 pi square meter per second square is about 4 meter per second square. And the one cycle to complete one cycle of acceleration. It takes about 1 second. Then it's okay. And after this checking, then we are confident that these plots are correct. And here are some references. The first one is the Seismic Design Code of Building. It's published in 2011 by the Ministry of Interior. Another reference is ordinary differential equation. You can find out this reference from any textbook of engineering mathematics. Another reference is Laplace transform. Is also, you can find of this reference from any textbook of engineering mathematics. And this unit we talk about fundamental vibration period. And it's very important because seismic forces depends on fundamental vibration period. Therefore, we have to have a very good management about the fundamental vibration period of a structure. That's all for this unit. Thank you. See you next time. Bye-bye.